Hi everyone, this is the third video under the series of videos which I created for the geometric design. This covers the portion gradients and grade compensation. Railways, they have a great ability to hold very heavy loads. This advantage is only significant when the tracks are fairly level. As soon as the gradient increases, it adds drag to the train, thereby the tonnage that can be held is greatly diminishing. Gradient climbing is a problem faced by railway systems because it is going to affect the load carrying capacity and also the operational speed. There are various techniques to overcome the steep gradients, like attaching additional banking engines or replacing the engine with a more powerful or heavier engine for the duration of the steep speed, or by dividing the load or splitting the train or strengthening the track. These are the various options. Then we can make some changes in the geometric design also. So this figure, it's a spiral viaduct near Brussels in Switzerland, where you can see the track is going in the same direction, but still a spiral curve is provided in order to have a smooth gradient. Okay. And another example you can search in Google is horseshoe curve near Pennsylvania. Then here there is this is the Pikes Peak Railway, where it's an example of rack railway. In the case of rack railway, there will be a tooth rail between the bearing rails which engages with the coke wheel under the locomotive for very steep slopes. Then this is another example of zigzag railway. So there are various means for dealing with the steep gradients. So let's see the different types of gradients and all these details in this video. Welcome you all to this video. Let's see the definition for a gradient. Any departure of the track from the level is known as the grade or gradient. There are different means of representing that. An upward gradient or a rising gradient is the one when the track rises in the direction of movement of the traffic, and a downward or falling gradient is the one when the track falls in the direction of traffic movement. So it can be measured or it can be represented in two ways. One is by the extent of rise or fall in 100 units horizontal distance, or it can be represented by the horizontal distance traveled for a rise or fall in 1 unit. So let's see this alignment, which rises 2 meter in a horizontal distance of 50 meter, would either be represented as 4 in 100 or 4%, or it can also be represented as 1 in 25. Gradients are provided on the track due to the following reason: to provide a uniform rate of rise or fall as far as possible. Then, to the extent possible, the natural contours of the ground is followed, and also to reach the various stations that are located at different elevations, and to reduce the cost of earthwork. So in the below figure, you can see that the cutting and embankment are so balanced that the cost of earthwork can be minimized too by providing such a kind of gradient. Various gradients used on railway tracks can be classified under the following heads. So there are four types basically. One is the ruling gradient, then there is momentum gradient, then other type is a pusher or helper gradient, then the gradients that to be provided in the station yards. So let's see all these in detail in the coming slides. Ruling gradient. The ruling gradient, or it can be also called by the name the design gradient, for which the section is being designed, because it determines the basic performance of the locomotive, and at the same time it tries to look at the total amount of load which the locomotive can take up along with it while negotiating any gradient without any loss in the speed of the movement. So it is the steepest gradient that exists in a section, which determines the maximum load that can be held by the locomotive. Indian standards do not specify any fixed ruling gradient due to the varying nature of the country, speed and traffic. So generally, with one locomotive train, the following gradient are adopted. For plain terrain, it varies in the range of 1 in 150 to 1 in 200, whereas for hilly terrain, it is in the range of 1 in 100 to 1 in 150. So as a rule, once a ruling gradient is specified for a section, there should not be any gradient which is steeper than that. So that is the importance of ruling gradient. So other gradient should be flatter than the ruling gradient, and usually it is defined as a gradient where the fully loaded train can haul at maximum power of a given engine without the help of extra engine, or by reducing the train load, or by reducing the speed of the train. Momentum gradient. This momentum gradient I can explain with the help of this figure. So here a cyclist is traveling through a valley. So a valley, a falling gradient is usually followed by a rising gradient. So one cyclist, while coming down a falling gradient, acquires sufficient momentum. So this momentum gives additional kinetic energy that helps him, or that enables him to overcome the steeper gradient following that. So similar way, this can be applied in the case of trains also. So this momentum gradient is achieved due to that particular location. The momentum gradient is achieved due to the favorable position of it on the track. So here you can see in this, the rising gradient always follows the falling gradient, so that the momentum acquired during the falling gradient can be effectively used for negotiating the further ascending gradient. Usually the rising gradient will be more than the ruling gradient. So ruling gradient is the maximum permitted, but in this particular case, the gradient can be more steeper than the ruling gradient, because it is gaining sufficient momentum, and this momentum acquired can be effectively used, or it gives additional kinetic energy which can be effectively used to overcome the steeper gradients. Only one condition is there: the train should not be stopped in the territory where it acquires sufficient momentum to negotiate the further rising gradient. So there should not be any signals or stops should be provided, and there should not be any station that should come in the valley side. For example, it is following a falling gradient, and if a station is provided in between, then it cannot gain the sufficient momentum. So in that case, the rising gradient should be converted to the ruling gradient. Let me show you a video of Gol Gumbaz Express, which is at Bijapur, Karnataka. So it's a big example of momentum gradient. Let's see this video. So a rising gradient is following a falling gradient. So the momentum it gains during this falling gradient is effectively used to overcome or to negotiate the further ascending gradient. So here the rising gradient provided is more than that of the ruling gradient. So when defining the ruling gradient, I told you that the maximum gradient that can be provided should be the ruling gradient. Since here, if you can see, there is no extra power required there, the same engine is being used. So the momentum that it achieves during the falling gradient is effectively used for the rising gradient. So it is at the location Bhairanaikanahalli, which is near Bijapur, Karnataka. So pusher or helper gradient. So I told you the ruling gradient is the one for which we are designing the section, and we are deciding the load the train can carry, or the speed with which the train can move through the given section. So no gradient should be more than this ruling gradient, but at some location we are forced to provide the gradient more than this ruling gradient. So how to overcome this pusher gradient, or how to negotiate the gradients which are more than this ruling gradient? So one way we have seen in the case of momentum gradient, where the train achieves momentum by coming down a falling gradient, can be used for climbing the rising gradient following it. And another way is with the help of pusher engines. So the gradients, when it is more than that of the ruling gradient, so usually it is in the range of 1 in 100 or 1 in 75 or even more than that, additional engines will be provided. So that usually in hilly areas, the rate of rise of terrain becomes very important when trying to reduce the length of the railway line. So additional engines attached for helping it to climb the gradient, they are also called by the name pusher gradient. So instead of limiting the train load for the entire section, it is more easier and economical to run the train on the basis of maximum load that the engine can carry, and only on the portion where it needs help, or the portion where the gradient is more than that, we can provide a pusher engine, okay, or we can provide an additional engine. So thereby we can reduce the overall cost of operational cost can be reduced thereby. This type of gradient is known by the name assisting gradient, pusher gradient, or backing gradient. So it makes operation more easy and economical. So we don't have to reduce the length of the railway section. We don't have to reduce the load it can carry. It can operate under the design load, and it can operate for the given length. But only thing is, at that particular location where the gradient is steeper than the ruling gradient, an additional engine can be provided so that it could negotiate the extra gradient. So you can see a lot of examples here in the Western Ghats and also in the mountain railways. Say in the Darjeeling, there are gradients which is steeper in the range of 1 in 25, or in Western Ghats in the broad gauge itself you can see an example which is 1 in 37, where it is in Budni Barkhara section. So where more engines will be used to climb that particular gradient. Say this figure will show you. You can see here there are 4 engines. This is an older one only. So more engines can be attached at that particular portion to climb the steeper gradients. The gradients that to be provided in the station yards. So it is based on 2 factors. So usually the gradients are kept flat as far as possible. So the maximum gradient that can be provided is 1 in 400. That too depends on 2 factors. One is to reduce the additional resistive force required to start a locomotive, because at the starting time the resistance offered by the gradient will be twice that of the normal gradient. So it should be kept as flat as possible, thereby there is no additional resistive force required to start a locomotive. Another one is to prevent the standing vehicle from rolling and moving away from the yard. So here in the figure itself you can see there will be lot of stop wagons in the station yards. Okay, so if the gradient there is steeper, then the stopped wagons can roll and can move away from the yard. So it should be made as flat as possible. But for the purpose of drainage, the minimum gradient to be provided, and it is usually 1 in 1000. Grade compensation. So this usually comes when the gradient is associated with a circular curve, or if at a particular location if a curve, circular curve as well as a gradient is there, at that location we have to reduce the gradient, even though we have specified a certain values for the ruling gradient, the pusher gradient, etc. We have to limit those values if a curve is coming at a particular gradient location. Okay, so in the case of circular curves, we have seen the safe speed with which it can negotiate. We have also seen the equilibrium speed for which we designed the circular curve. So in that particular cases, we have to reduce the speed of the train when negotiating the circular curve due to the safety aspect. So when a curve is coming, so curve provides extra resistance to the movement of train on gradients. So the ruling gradient is a maximum gradient we have defined. The ruling gradient is a maximum gradient on a particular section. But if a curve lies on the ruling gradient, the resistance due to the gradient is increased by that due to the curvature, and this further increases the resistance beyond the ruling gradient. Okay. So in order to avoid the resistance beyond the allowable limits, the gradients are reduced on the curves, and this reduction in gradient is known as the grade compensation. So the curve resistance is expressed as a percentage per degree of the curve, and the curve resistance is greater at lower speeds. So on broad gauge track in India, the compensation for curve is given as 0.04 percentage per degree of the curve for broad gauge, or it can also be in terms of radius. It should be 70 by R, whichever is minimum. Then when considering the meter gauge track, it should be 0.03 percentage, and in terms of radius it is 52.5 by R for meter gauge. Then for narrow gauge it is given as 0.02 percentage per degree of curve, or in terms of radius it is 35 by R. So this whichever is minimum we have to take. So for broad gauge, for compensating the curvature, a grade compensation of 0.04 percentage per degree of the curve to be provided, or if the radius is given then it should be 70 by R. Or you can calculate both this as per degree and radius, then whichever is minimum, that we have to prefer. So grade compensation is usually being provided at curves, or grade compensation on curves. So find the steepest gradient on a 2-degree curve for a broad gauge line with a ruling gradient of 1 in 200. So the ruling gradient is given. It's a broad gauge line. Then the steepest gradient on a 2-degree curve. So the curve there is 2 degree. So accordingly we have to design the grade compensation. So the ruling gradient is given as 0.5 percentage. So the compensation required for a 2-degree curve is 0.04 percentage of the degree of the curve, which means 0.08 percentage. So the compensated grade will be the ruling gradient minus the compensation for the 2-degree curve, which is 0.08. So the difference between that will give you the compensated grade. So which is 0.42 percentage, or I can write that is in 1 in 238. So the cheapest gradient that can be provided on a curve track of 2-degree curve is 1 in 238. So even though it is specified as 1 in 200, we cannot provide that ruling gradient because of the curve that is coming there. So we have to reduce the gradient to 1 in 238. Hope this is clear to you. Thank you. If you have any further doubts, you can contact me. You can either write to me through my Gmail, or you can contact me. That's all for today's video. Thank you once again.